Hello guys, this is Dr. Miles from DMSA Tutors. In this video we are going to focus on integrated weight law for first order reaction. Let's consider this chemical equation. A gives B plus C. The rate of this reaction can be written this way: minus the A dt equals minus the B dt equals plus the C dt. This represents the rate of this reaction. But for weight law for this reaction can only be written this way. Since weight law uses only the condition of the reactant, let's assume this reaction has been experimented to be first order reaction. It means that we have raised power 1 here. Since R and this one, they are representing the rate of reaction, it means we can now equate the two of them. So therefore we can have minus the A dt equals Ka. Let the condition of A equals C. Therefore we have minus the C dt equals Kc. Now let's rearrange this guy so that both sides will contain differential signs. So therefore we have minus the C all over C equals K dt. So therefore we have the C all over C equals minus K dt. Okay, now let's get rid of the differential signs by integrating both sides. So therefore we have integration of the C over C equals minus integration of K dt. In mathematics, whenever we want to integrate the C over C, let's say we have integral of 1 over x dx, which is also same thing as the x over x. So whenever we are integrating this guy, we always have then x plus c. So and whenever we are integrating the constants, let's say we are integrating integral of 2 dx, so we always have 2x plus c. So let's note this one. The integral of c over c, as c is changing from its initial state to final state, and integral of k dt, as t is changing from time 0 to time t in the future. So therefore we have ln c as c is changing from initial state to final state equals integral of minus k dt is minus kt, as t is changing from its initial state to final state. So from time 0 to time t in the future. We have lower boundaries and upper boundaries. Okay, now let's express the boundaries. Ln c, as c is changing from initial state to final state, so we subtract the upper boundaries from the lower boundaries. So therefore here we represent the upper boundary first, then we subtract the lower boundaries from it. So therefore we have ln c f minus ln c initial. and this equals to, and for minus kt, if we input the upper boundaries, so we have minus k t minus k 0. We have ln c final minus ln c initial equals minus kt, because the remaining have gotten to 0 out. Alright, so this is the integrated weight law for first order reaction, and that is ln c final minus ln c initial equals minus kt. Sometimes this can be represented in a log form. Let's show the relationship between ln x and log x. Okay. Ln x equals 2.303 log x. It means that for this integrated weight law, if we want to change the ln to log, what we have to do is that to replace the ln c final and ln c initial with 2.3 log c final and 2.303 log c initial. So we have 2.303 log c final minus 2.303 log c initial equals minus kt. And if we divide both sides, we divide through by 2.303, we have log c final minus log c initial equals minus kt over 2.303. So this formula also works for first order reaction. We want to use log instead of ln. Okay. So we have log c final minus log c initial equals minus kt all over 2.303. So now we have two formulas. The first one is if we are using ln. If we are using ln, we have ln c final minus ln c initial equals minus kt. And this also equivalent to log form, in form of log c final minus log c initial equals minus kt over 2.303. The two formulas are correct. Let's talk about the graphical representation for first order reaction. Okay, from ln c final, the final concentration minus ln c initial equals minus kt. In this form now, if we want to represent it in a graphical form, it means we have to rewrite this weight law to look like equation of a straight line. Y equals mx plus c. And in that sense, we have to write ln c final. In that sense, we have to write it this way. Ln c final equals minus kt plus ln c. Ln c final represents the y-axis, and ln c initial is the intercept, while minus k represents the slope, and t, the time, represents the x-axis. So here now we have length C final, and here we have the time. So this is the concentration versus time graph. In that sense now, means since the slope is negative, minus k, we face down, and we have so here is our intercept, that's length C initial, and the slope here is our minus k. So it means that y equals ln C final, m equals minus k, x equals t, that is the time, and c, the intercept, represents the ln C initial. Let me call attention to something. If you are using a log instead of ln, you have something like this. Since log C final minus log C initial equals minus kt over 2.303. Therefore, this guy has equation of a straight line, so we have log C final equals minus kt over 2.303 plus log C initial. The y-axis is log C final, the x-axis is the t, then the slope will be minus k over 2.303, and here still represents log C initial, that's the intercept. Alright, this does the difference between using a log and using a ln. Also, you may see another forms of the integrated rate law for first order reaction this way, as log C final minus log C initial equals minus kt. This thing minus kt over 2.303. Write this equation: log C initial minus log C initial plus log C final equals minus kt over 2.303. So let multiply through by negative. So by doing that, we have log C initial minus log C final equals kt over 2.303. Alright, now let's Ci, the C initial, equals A, and C final equals A minus X, where X is the amount of concentration that has been consumed. Amount of concentration consumed already. Log A minus X equals kt over 2.303. And therefore we have, from law of logarithm, log A minus B equals log A over B. So therefore we have log A all over A minus X equals KT over 2.303. So this formula also works for first order reaction. Let's talk about the half-life for first order reaction. Half-life for first order reaction is the time taken for a particular concentration of a reactant to become half of its original size. So the time taken is called the half-life. And therefore we say that at half-life, the final concentration equals half of initial, that's Ci over 2. And from ln C final minus ln C initial equals minus KT. It means that at half-life, what we have is ln Ci over 2, because C final already becomes Ci over 2, minus ln Ci equals minus K T half-life. Therefore, we have ln Ci minus ln 2 minus ln Ci equals minus K T half-life. This guy can cancel the gas out, and we have minus ln 2 equals minus K T half-life. And also, the negative sign can cancel negative sign. So we have ln 2 equals KT half-life. So half-life becomes ln 2 over K. And ln 2 is 0.693 over K. So half-life of the first order reaction equals half-life equals 0.693 over the rate constant. So here we can conclude that the half-life of a first order reaction is independent on initial concentration of the reactant. But the rate of a first order reaction depends on initial concentration of the reactant. The reactant. And always, the half-life is always inversely proportional to the rate constant. Alright, take care of yourself.